maybe we call E-phase question. Okay? Yeah? Okay, so I'm going to try to move on to the rest. Oh, I replied to you that I don't know what diopters are, right? You know what diopters are now? Okay, we still don't know what diopters are. Okay, so I think that's where we left off. Can someone still get farsightedness even if they are young? Yeah, totally possible. People can get all sorts of illnesses, all sorts of disorders, even at a very young age. Yeah? It's just that the propensity for such illnesses and diseases increases as you get older because your ability of your cells to recover itself, to produce a new healthier version, fails to happen. Okay, let's look at time use question. What happens when the focal point lands on the retina but not on the macula lutea? We don't need to mention how the person sees upright image, right? Okay, so I believe in your textbook they mentioned one area called the macula lutea, right? That area, think of it as just a point that has a lot of photoreceptors concentrated with colors. Does the focal point need to exactly land on that point? Not necessarily, but I would say most usually it lands around the area. So that area, that region has the most color receptors on. That's why if light, okay, I think you all won't believe this, but if that is where a lot of color receptors are, actually as you move away to the sides of your eyeballs, it starts to have less and less color receptors. So actually your vision on your right and your left, if you just look straight forward, actually it's black and white. But you don't believe me, right? The only way to test yourself is if your friend holds up something of color to your right or to your left, and in your periphery vision, you tell them what the color is. You're going to have a tough time telling and discerning what the color is. Because the light is coming in from an angle, is touching parts of your photoreceptors, they don't detect color. You can try that now. At least that day in 403, when you're all wearing their house keys, and you're trying to guess what each other's house keys are, they actually had trouble guessing the correct color from the periphery vision. But the moment you start glancing that way, and the light starts to land on the areas where there are color receptors, then you can detect the color very well. Okay? So you can try that yourself. Just at the corner of your eye, you guess what the color of an item is. We don't need to measure how a person sees an upright image, not in the context of bio. But I think if you have understanding of physics, how light refracts and bends, you would understand this, but we're not required to explain it. Xiong asks, if you unfocus, space out your eyes, and then walk. Oh wait, I felt like you asked this question. I answered this question before, right? This was a very interesting question. So actually, could you unfocus and space out? What are you actually doing? You're actually just relaxing your ciliary muscles to the max. Yeah? You're looking at me right now, I suspect you're not fully relaxed yet. Okay? I think if you look beyond me to the whiteboard, you're relaxing a little bit more. I think you're fully relaxed when you're staring at something super far away. For example, out into the distance. Yeah? So I think even if you look at that tree over there outside, the things beyond the tree should appear blurry to you. Right? That means you have not relaxed your fullest yet. You know you've relaxed your fullest when you are staring far beyond something and you cannot quite break off any more image and make it any more blur any further out. That means you've relaxed the furthest out. So that means actually, in truth, you looking at me right now is not your most maximum relaxed state for your ciliary muscles. It is not at its thinnest yet. Okay? I look like I've just confused someone. Okay, next up, Nicole Tan's question. If spectacle lenses are concave, meaning that they bend inwards, why are contact lenses convex instead? That is a good question. I have no idea why it's convex. Let me think up. Okay, I'm not exactly sure if we might consider your contact lenses convex in a conventional sense, because your contact lenses are just a single piece, right? Whereas my lenses that I've been working with, the convex lenses I work with, they were bent this way on both sides. So physics-wise, I cannot say for certain that your contact lenses are functioning the same way as a convex lens would. It could be. It could also be that because it's in direct contact of at your cornea area, that the bending of light, you do not require diverging of light. I think when you wear a lens right in front of you, because there's still a distance away from your eyeball, it serves a slightly different function to try to ensure that light that is diverging too much, converging too much, the divergence will be more compensated. So physics-wise, I'm not too sure if your contact lens are truly convex in nature. When asked, when the light is landing on the retina to achieve a focus image, does it just refer to the fovea specifically? Because the fovea is directly behind the lens. Okay. Land on the fovea is the best. Sharpest, clearest, best, most color. But you can land outside it. Your retina is full of photoreceptors. But more towards the edges of your eyeball, like the sides of the eyeball, you have less and less colored photoreceptors. That's when color isn't quite apparent anymore. That's why you look at things head on, or at least turn your eyeball so that you can look at the subject coming in straight into your eyeballs. Yishen asks, whoa, yeah, I think there are many questions here, Yishen. As you can see, lens of glasses, when you're wearing them, work as the opposite. So when we look at people's eyes through their glasses, how does the perception of their eye change? Okay, what do you mean? You can see the lenses of glasses work as... Yes.
So if I go to this side, then does it mean that it's converged?
Oh, I don't think so, because the lens is concave on both sides. So it should function the same way regardless of which way the spectacles enters. I guess we can do a simple test. You take out your specs and you flip it around. Do you still see a clear image? Okay, if it's not clear, that means my theory is wrong. Okay, it's still clear to me. Yeah, so I think it should work either way. Yeah.
But then how is those people when you wear glasses, then their eyes are very big or very small? Like one is smaller than the actual eyes.
Oh, I think it has to do with, long time ago in lower GH, where you learn about refraction, how when you look at something in the water, then it looks like they are slightly higher than it is because of refraction. I think it's likely that's what's happening. When you look at someone's eyeball, likely the refraction causes you to perceive that the person's eyeball is bigger. I think that happens when your lenses get bigger and bigger and bigger. For us, we all still look quite normal. Okay. Last term, someone said their degree go up to 600 plus. You 600 plus. Was there someone that top Pratisha? Okay, top Pratisha, 800 plus. 700 plus. Okay. Anyone in the 1,000 range? Okay, that's good, Okay. But you're wearing contact lenses? Is it, are your contact lens, I don't know, have you compared with anyone else? Is it like very thick? You never compare before, okay? If you have anyone to compare, you go and see, I'm not sure how much of a difference each contact lens will look like. Can far-sighted people exercise their ciliary muscles so that their vision becomes normal? I don't know. That's a good question. I mean, with every muscle, we can technically exercise it all. So I honestly don't know whether you can exercise to make it better. That's a good question. Maybe there are. Maybe there are. How can I cure my short-sightedness with exercise to reshape my eyeballs? I don't know. Give it a good bounce. I really don't know how. I don't think there's a way to reshape your eyeballs. Not that we know of. Perhaps this is something researchers are still trying to find out. I honestly don't know. Finally, when you use a flashlight for brain gate tests, how do you know it's not because the patient's sensory receptors are swelled? That's a good point. So when they do that test, after you get a concussion, they're not just exactly testing whether you're brain dead or not. They're testing whether the nervous system is damaged to a certain extent. So it could be that sensory neurons have been damaged. Okay? But that's usually one of the tests they do when you get some sort of concussion in the head. Jane asks, do the blood vessels block the photoreceptors? I don't think so, because I think anatomically how it's arranged is such that it's photoreceptors first, then the blood vessels behind. Correct. So I can't remember how exactly it works. It's not because the blood vessels are sort of in front. I I think it's because of the way light bounces around that ends up looking as though that you end up casting a shadow within your eyeball. So it's the way the light reflects within your eye. How do eye drops work? What do you mean by that question? I have limited knowledge on eye drops. Let me think. We set for quiz 1, right? We all set for quiz 1, right? So there's one MCQ question on eye drops, right?
What?
Huh? Don't have? Have, there's one MCQ question. It's just a graph. Then after I ask you about eye drops. Yeah. Honestly, the context did not matter at all. I was just trying to mask it to make it look a bit tougher. Okay, but the eye drops question, I went to research a bit, so that's why I learned about eye drops. Eye drops, sometimes you can find enzymes inside eye drops. So sometimes what you find inside eye drops is that when you put inside your eye, it serves to replenish the enzymes that are not there, digest some of the bacteria, pathogens that are running around the surface. I believe eye drops also serve as lubricants. Can you imagine every day you blink how many times? Imagine without any lubricant, the more times you blink, the more you're going to shear off layers and layers of your conjunctiva, after that your sclera. The more times you blink, right, the more layers will come off. Yeah? So I think it serves as a lubricant. It also serves to enzymes to digest certain bad things on the surface. I believe there are other functions, but I'm not too aware of those other functions. I really put eye drops. I don't know how often do you all put eye drops. Anyone puts eye drops? No? Maybe it's a old people thing. Sorry. Sachi, you were about to raise your hand. Okay, you don't know? Okay. Yeah. Maybe, I don't know. Yeah, I will see older people put it. They say their eyes very dry. I need to like talk about it. I'm not sure how it works, but I recall that my grandma used to put eye drops. And the doctor says it's to help with pressure relief. Says that it helps with the pressure of the eyeball. Not exactly sure how it helps. Kali asks, what is considered normal light? And will the iris muscle relax or contract to normal light? Kali, in what context do you encounter the word normal light? Oh, okay. And will the iris muscles relax or contract in normal light? The iris muscles, not the iris muscles, I think it's a bit broad to say iris muscles relax or contract because you have to refer to either the circular or radial. But let's talk about pupil. The pupil can either be smaller or bigger, right? Okay. So I think what we presented to you is the simplest of understanding. The most extreme ends. Small, big. In reality, it's a continuum. Our eyes adjust how much each set of muscles contract and relax to adjust the size accordingly. Same for the thickness of our lens. So what is considered normal light? I would say we will not present to you such a situation in the exam context because normal is a little bit hard to discern. But if we do put normal, it is likely relative to something else. So I think it is easier to understand on the relatively speaking terms if you want to explain which one is contracting, which one is relaxing. Okay? So usually we will say something along the lines of it's very dark, or it's dim, or it's very bright. Or if someone does say normal, I think what they will usually do is that they'll put in relation to something else. Likely, I think it may be something dimmer. Then the normal condition may be considered the bright condition. Okay? So we ask, what brings about astigmatism? Sorry, Zoe, I don't know. This one I really don't know. I don't even know what person feels when they get astigmatism. Hey, sorry, Valentina is still recording. Okay, thank you. Do you have astigmatism? Okay, what does it feel like? I don't know what it means to get astigmatism. I hear before lah.
Like when you look at light, then you appear like
Oh, a streak, or like you see additional. Wait, when you look at light, you see additional streaks coming out. Wait, but I see that too. Like, so do I have astigmatism?
yeah, it's quite common.
Okay, I don't know the biology behind it. I honestly don't know. But I think a quick Google should be able to give you an understanding of it. Now that you know how all the parts work. But if you you want to make an educated guess. If what Zoe says of the symptom of astigmatism is that light disperses, and I think there are only two areas that will be affected. It's either something to do with your lens or your photoreceptors. Because the light is dispersing in a way that is not quite ideal. What happens to the eye when you have conjunctivitis? Usually, if you see a vitis behind, means there is some sort of a bacterial infection of some sort. So someone who has conjunctivitis means that that layer that is wrapping around your eyeball gets infected. If it gets infected, likely you also see that your sclera looks red. But actually, it's not your sclera per se that's red. It's the conjunctiva, the transparent layer that is now becoming very red. What part is most commonly damaged when someone is blind? When someone is blind, blindness got different extent. One could say that 3/4 of our class here is 3/4 blind or half blind, right? With the spectacles we are wearing. So actually also when you talk about people with blindness, I had a misconception last time that when you say someone is blind, that it is complete darkness. But actually that's not really the case. I went for a particular workshop conducted by people who cannot see, and they described to us there are varying levels of blindness. For some people, it's really just pitch black. For a lot of people that are blind, it is really a case of extreme blurriness. You can still make out that there is light in the room, but it's extreme blurriness. You cannot make out quite anything else. And then there's another case where it's complete darkness. So varying levels of blindness. What is most commonly damaged usually is the photoreceptors. They are not functioning. Why does your eye get sensitive to light when you are sleep deprived? Why? When you are sleep deprived, usually you are depriving your body the ability to recover, and then from all the chemicals, waste products that are accumulating in your brain. That can affect your homeostasis process. Why do you get extra sensitive? I'm not exactly sure. It could be that homeostatically you are not maintaining that well anymore. It could be that now anything light that's coming in is too much for your body to handle now. I'm not exactly sure. But I think usually when you're sleep deprived, it's your homeostatic systems, your brain that's not having enough ability to recover. So likely it has to do with your brain, not so much the eye anymore. Okay. Oh, still a new cards. Serene, this was put in today. If it is really dark blur, or you close one eye and you don't really have that perception, your irises still know. What do you mean by no? Oh, sorry, let me repeat a bit more. Like if you can't tell the difference at all, but your irises still contract, relax accordingly. Why not contract relaxation of the irises signal to the brain how far away an object is? Oh, but you know when our iris muscles contract or relax, right, to adjust the pupil size, it's really just adjusting based on the light intensity, not so much how light bends, right? Technically, I could have an object that is close to you, right in front of your eyeball, in the dark and in a bright environment. And that changes how close or far an object is, right? That will affect the lens thickness. Sorry? Okay, so are you saying, so do I change all the iris and ciliary muscles? Okay, so are you asking, why can't the ciliary muscles contract, relax, signal to the brain how far away an object is? Oh, because the ciliary muscles aren't receptors. They cannot detect light, right? The ciliary muscles adjusting themselves is the end outcome of the photoreceptors in your eye detecting the light. So you cannot expect the muscles to signal to the brain because the muscles are the effectors. They are not the sensors, they are not the receptors, so they cannot detect. Does that answer your question? One thing I'm very curious about your question is, if you cover one eye, will your eye that's covered adjust accordingly based on what you are seeing? That is a question I'm not very sure about. Is that what your question is asking? Okay, it's not. Okay, then a new question came from my own head. So what other aspects have I not answered? The knowing part? Okay, if it's really dark or blur, or you close one eye and you don't really have the depth perception, do your iris, do your ciliary muscles still know? Okay, I can't tell the difference, but oh yeah, okay. I think, again, my answer to you would be ciliary muscles cannot detect. They cannot tell the difference between something close or far. But it can respond if something is close or far based on what the photoreceptors detect. Sorry, say again.
You can't like tell like the brain processes your muscles do like contract.
You have to speak up a bit.
If you can't tell whether like if you don't have that perception, do your muscles do like contract and relax?
Oh, if you don't have depth perception.
Like you can't tell what it is.
Okay. But whether you can. Oh, okay. Are you saying that if you cover one eye, now your depth perception is gone, is it? So you cannot tell whether it is near or far. Ah, okay. Still can. So, as an individual, you can perceive depth with both eyes. But individually, each eye, what is coming in that affects whether the ciliary muscles will contract or relax is the angle at which light is coming in. Okay? Not depth perception, just the angle at which light is coming in. If you have an object very close to you, the object light rays will be diverging into your eyeballs. If it's further away, it's coming in more parallel. But that is distinct from whether you have one or two eyeballs. So your eye can still adjust based on how light reflects into your eye, not depth perception. Depth perception is what your brain perceives when you have two eyes. What I'm curious about is if you cover one eye and you look at something close, I wonder if your other eye that is not seeing this object that's close to you adjusts its ciliary muscles also. That one I'm not exactly sure. I also don't know how we might conduct a test to see that process. Okay, so that closes off the nervous system chapter. Today, we're going to ease into the respiratory system. I will begin first with the parts of the respiratory system that I hope that are a little bit more familiar to you. Some parts you could touch, at least directly under your skin, so you can still feel all those parts. Okay, so we're going to start off with that today, the various parts of the respiratory system. We expect you to know the various parts that we named out. For example, larynx, trachea, bronchi, bronchioles, alveoli, capillaries, so on and so forth. I just want to check, because nowadays primary school is very different. You all did not learn this in primary school, right? Parts of your respiratory system. You all take. Oh, primary school, you know what? Oh, okay. Primary school you all learned before. How come? I don't know, I get sensing some of you all know what bronchioles, bronchi are. Do you all learn this in OJH? I don't recall teaching you that. No, right? Oh, so primary school you all learn a little bit. Did not? Okay. Different primary school. So here, structurally, all these parts you sort of know one. Alright, you sort of expect, logically speaking, that these parts should be there. Okay, so that's where we will start off today. And briefly, we're going to learn about the characteristics of these various parts. You have a similar diagram in your textbook. You can open your notes to search for this part as we slowly run through the parts. Then I can show you what you are touching, the various parts of your body. Right now, from the sound of it, my sinuses are quite filled with mucus. Actually, your sinuses, your nose area is quite linked to your ear canals also. So, have you ever felt that when you have a flu, sometimes your hearing is affected? Yeah, because your mucus can actually go all the way and clog almost reaching your ear canal area. Sometimes when you blow your nose, right, when you're having a very bad flu, you you feel like your ears clear also. Ever had that feeling? Or maybe it's just me. Okay, so today I'm going to start off with some parts of the respiratory system, and then I'm going to cover some of the parts that you were expected to learn by yourself about how you breathe. Let's begin first with the most obvious that upon scanning all of us have, your nose. Yeah, your nose is the very first part, or at least you know of as the part of the respiratory system that allows you to get air in. Right? So that's your nose. Your nostrils, you have two of them. Now let's go a little bit deeper in, because you realize that if someone were to pinch your nose, you can still breathe, right? That's because you can breathe through your mouth. So that means to say, technically there are two channels that air can go in. So let's look at the two channels. The first channel, if you breathe through your nose, you'll go down a tube at the back called the pharynx. If you breathe through your mouth, you go through the front, called the larynx. What this diagram does not show is where your esophagus is. You remember lower GH, your esophagus? Okay, let's look at all three parts together so that you can draw in where the esophagus will be. Esophagus, larynx, so on and so forth. I think this is a pretty good image. If you can find it on Google, it will also help you. And we can talk a little bit about choking. Okay, this is broadly what you will see typically in diagrams. Where is your pharynx? Your pharynx would be up here, right, where you're breathing in from. If you breathe through your nose, breathe through your mouth, it should go down this type over here, the larynx, so the lower tube. You actually have esophagus, where the food will go in. So if we look at how everything connects up, what your textbook shows is just minus the esophagus behind. Okay, you look at your diagram in the textbook, it does not have the esophagus. That's it. Or in the SLS, if we look at this particular image over here, what you do not see is the esophagus exactly. You can sort of make out that the esophagus, they are trying to branch down to the esophagus somewhere over here. To zoom into the diagram, you see behind, over here, it looks like it's branching out to somewhere, right? Okay, it's not connecting to this pipe over here. It's going behind. So you have actually another tube going behind your trachea. So that means to say, this tube over here, what exactly are you feeling over here? I used to think that this is where your food tube is. I used to think that this is the esophagus, right? Because after all, when you swallow, right, then you feel like the muscle go up and down, right? But it's not quite related to your esophagus. This tube that you feel over here is not your esophagus. Your esophagus is behind this tube over here. This tube instead is used for breathing. Okay, so you just take note of that. This tube, in fact, if you feel this tube, what you are feeling is this thing called the trachea. The trachea is the main big tube going down into your body that will eventually branch out into two. So what you feel here is the beginnings of your trachea. I'd like you to feel your trachea. Can you feel that there are many layers to it? Yeah? Don't squeeze too hard. Let students squeeze and then choke and start coughing. And feel? Right? It's not a smooth tube, right? Can you feel like layers and layers? So you should have felt something like that. You should have felt something like, like bumps, right? Feel that? Yeah? Okay, that's because, right, what you're feeling actually, each lump that's coming out is cartilage. Cartilage that goes one round. Not fully one round, but it kind of wraps around trachea. So cartilage. This is from the side view. So I'm drawing cartilage. Your trachea is actually soft, just like your swallowing tube, your esophagus. But we cannot let it be soft, right? If you are breathing in and out, if that tube is soft, it will collapse on itself and you cannot let air flow through. So we need to find a way to let the air tube constantly be open. So actually that soft trachea is attached to these cartilage to keep it open. So the trachea is actually a soft tube that is wrapped around by cartilage. From the side view, it looks like that. From the top view, let's say if this is your front, if this is your front, and this is the back, and we're looking from the top down now, and let's say your head is gone, then the cartilage goes like that. It's just a C-shaped cartilage. It doesn't go one round through. Okay? It is C-shaped, and then there's that tube that allows air to go through. This one will be a complete circle, yeah. Okay? This way air goes in and out from, and the cartilage is a C-shaped cartilage. I want to make an educated guess. Why do you think the cartilage is C-shaped and not one round through? Take a guess. Why is it C-shaped, not one round through? There's an anatomical reason for it. Facilitates the function of another part. Yeah, thank you, Santosh. It's where the esophagus is. Yeah? You see, if it's not C-shaped and it goes one round through, your poor esophagus behind, imagine this is your esophagus behind, that is normally not expanded out unless food is going down. Yeah, imagine you swallow something damn big, it goes down, then it gets stuck at a C-shaped cartilage ring. Right? Cannot go through. So our body way around it is that let's make it C-shaped so that let's say if something big goes down, it's fine. As it goes down and this expands out, it can push inwards to the flexible part of the trachea a little bit. And that's fine. After all, you're not supposed to eat and breathe at the same time. Yeah? It's supposed to happen separately. So that's fine. So that is the function and why it's C-shaped, if someone ever asks you. Okay, so several parts settled. We have the pharynx with the larynx. And take note that actually the pharynx and the larynx, it could go down the trachea, which is your front, or it could go down the back, which is your esophagus. Have you ever eaten through your nose before? I mean, technically can. If you suck things right back, I mean, I don't know, not. Okay, yeah. I mean, if you had the misfortune or had to go to the hospital, or you've been to hospitals before, you've seen that sometimes people are fed through the nose. So before. Okay, some patients, when you go to the hospital and they can no longer feed themselves, what they do is that they insert a tube up the nose, the nostril, down the pharynx, and you push it further down, and if you direct it, it can go down the esophagus. Yeah? And if it goes down the esophagus, that means to say it can feed liquid food through the nose. They don't usually put it through the mouth, the mouth, and then through the larynx, and then down the esophagus, to avoid the gag reflex. I mean, I'm sure you've had a situation where you gag, right? When something big goes down your throat, right? So to avoid the gag reflex, go through the nose. Other things, when you choke, what's actually happening? Goes down the wrong way, goes down the trachea, right? If you choke, it goes down the trachea. It normally happens when you're trying to do two things at once. Talking to your friend, eating, right? Oh, I tell you, this food is very hot. Then after that, the food goes down the wrong way. So when you choke, it's because it's going down the trachea, and your body is desperately trying to force it out. Can it force it out? Can. Actually, the trachea is muscular in nature. So this blue part that I've drawn, it has muscles. So it can help to contract and at least try to force the food out if you went down the wrong way. Last but not least, if you look at the trachea eventually needs to branch out into two to reach both sides of your lungs. Each tube, we call it a bronchi. Sorry, each tube is called bronchus, singular, plural, bronchi. So what's it good? Yeah, the trachea goes down, bronchus on each side, left bronchus, right bronchus, collectively we call them bronchi. And then you get to the familiar part of the body, your lungs. What is an interesting anatomical feature of your lungs is that it's not quite what you expect. Not sure if you can see in your textbook. Okay, when you look at your lungs, it looks as though there's an inside and an outside, right? Can you see that this diagram over here, they try to make it somewhat transparent, right? They try to make it somewhat transparent, and you can see sort of a lot of branches coming in, and then there's an outer layer, right? So when we look at your lungs is not just two balloon bags. Actually, the balloon bags within them contains many of the branches that branch out from the bronchi. Each bronchus will branch out even more to form many smaller tubes called bronchioles, branch out even more to form tiny little balloons called alveolus or alveoli for plural. Let's try to find a diagram that will be better for you. Okay, I think I have an old version of the textbook. You should have a newer version where I updated images. If you look at this diagram over here, it gives you a better representation if I were to take away the outer membrane of the lungs. See that the trachea branches off into the bronchus on both sides. Each bronchus branches off even more bronchioles, branches off even more eventually to these small little bubbles, small little balloons. Some of you may have heard of them as air sacs, but at least for level, I hope that you can use the word alveoli. If you see the word alveolus, it's referring to just one of the balloons. If you see the word alveoli, it's referring to many of them. If someone says alveolar air sacs, they're referring to alveoli, lots and lots of these small little bubbles. So broadly speaking, that is the channel, the pathway that air takes into and out of your lungs. So, okay, I know this activity is a rather simple one, but perhaps more for yourself. Would you copy paste this image? Need not upload it back on SLS. You could if you like to, so that you can share with each other. But roughly just have an idea of how air enters your lungs. Right? There are actually more than one way that air can enter your lungs. Not just through your nostrils, also through your mouth. If you like to, if you have a better diagram inside your textbook, you could use the diagram instead. Or you could use this diagram to draw arrows to trace the flow of air into your lungs. It should go all the way down to the final point, which is the air sacs or the alveoli. I see you got a question earlier. Ali? You should ask, if you look at the textbook, which one exactly is alveolus? Alveolus refers to one of those balls. Okay? Just one of those sacs. No, it refers to just one of them. Okay? Alveoli refers to many of them. So actually, very often we will say alveoli, the word alveoli. Yeah, the super tiny thing. So each one of these small little ones, that is one alveolus. Here, there are many alveoli. Okay? You can ask what exactly is cartilage? Yeah, it's a soft bone. a bone that is a little bit more flexible than the ones that your skeletal muscles are wrapping around. Your nose also, cartilage. Your ears also, cartilage. These are things that break down more easily also. Usually, fossilized remains, you do not find all these cartilage left behind. Does cartilage go back again? I think it's possible. I think it's possible. I've not heard that it cannot. I've not heard cannot. So it could be possible. Yes. Oh, so can food actually enter your lungs? Can. So if it really enters your lungs, how? Okay. So how? Well, there are various mechanisms that your lungs will respond. Everywhere of our body got immune system, right? So actually one way, your immune system, they start to try to break down whatever that went into your lungs. After all, as you are talking, you are breathing in, lots of pathogens, bad things are entering your lungs all the time. So actually our immune system, white blood cells are constantly trying to digest and break down all these bad things. Digest, break down already, then how? We absorb it into our system. Then like that we might as well eat through our respiratory system, right? No lah. So actually our body has a very interesting way of expelling all this. But I think how we can understand how our body is able to do that would be to look at the anatomy of our trachea. If you scroll down to this part of the textbook, also found inside the SLS. Okay, this is the trachea. You find that the trachea has muscle, call them smooth muscle. This muscle, as I say, could contract. Prevent yourself, if you do choke, something go down, have to contract, prevent things from going down further. When people have asthma attacks, actually that is also the part that's contracting. Anyone of you asthmatics? Okay. If you are asthmatic, what you will feel is that, hey, the region that's going down your airway feels very tight. That's because the trachea is contracting, preventing air from going down. Okay, so our trachea is made of muscle. That's the first thing. First region that can help to regulate things going in and out. We have the cartilage. It also helps to regulate, keep the airways always open. Last but not least, I'd like you to see this layer over here. You see the word ciliated epithelia? Epithelia means outermost layer. So as you can see, it is this black layer that they are pointing to, outermost. It is the word ciliated. Have you seen this word cilia before? See before? Okay, where have you heard the word cilia before? Small intestine. Huh? Hey, wrong, huh? Small intestine, what you all saw is villi. You're not cilia. Hey, where have you seen cilia before? You may have seen it before a long time ago in lower JH when we talk about bacteria. Bacterial cells have this extra tail, right? Okay. But anyway, cilia, how do you spell cilia? Okay, just one L. Cilia is microscopic hair. So, the inside of your trachea is hairy. Never quite felt it before, but it is hairy. Microscopic hair. Not hairy to the extent that you expect your head that kind of hairy, microscopic hairs. But they serve a very beautiful function. If this is your trachea, and if I were to make the microscopic hairs a bit bigger so we can visualize it, the microscopic hair is constantly engaged in this particular moving motion. It's very interesting. So if this is a cell of the epithelium, and you have this cilia, what it's doing is that it's constantly sweeping up. So it's a wave-like motion. It constantly sweep up, sweep up, sweep up. When you are sick and you have phlegm, it's not like the phlegm stays in there forever, right? Every while, periodically, you feel like you need to cough up the phlegm, right? That's because it's like a conveyor belt. All these cilia is working together, constantly sweeping upwards the mucus that has trapped any dirt, anything that has been digested by your immune system in the lungs, so that you can expel out the mucus eventually. Okay? And that being said, we actually need one more function of the trachea to be able to serve its function fully. Mucus. Right? There's no way we can trap dust, trap dirt, trap bacteria coming in, or anything that got stuck in our lungs and we want to get it out if there is nothing sticky to trap it. So it's mucus. We also need mucus. So actually, the epithelium, this layer, also come with cells that can produce mucus. They are excretory glands. Sorry, not excretory glands. What? Endocrine and exocrine glands. They are like exocrine glands. They produce mucus. So if I were to draw a hair, sometimes you'll find the cells of the epithelium, they will have glands that will secrete out mucus. Does your updated textbook come with that image? Yes. Yeah. Okay. Your textbook comes with this image over here. Okay. You see the word goblet cells? You can circle the word goblet cells. Those are the cells that produce mucus. Then you can also sort of see the microscopic heads at the very, very tip of these cells. Those are the cilia. Collectively, whatever we just learned, we can summarize it to say that this is the respiratory tract. The tract is like a pathway. And the tract consists of from the trachea, the bronchi, the bronchioles, to the alveolus. This is the tract that air takes in and out. How do we keep this tract constantly open and clear? Many ways. We have the C-shaped rings of cartilage that helps to keep the airways open. There's also a muscle layer. This smooth muscle layer, in the event of choking, can technically contract, prevent food or objects from going down the wrong way. Also can help to expel out these kind of objects. You also have cilia to constantly sweep out mucus that traps dust. And that means to say you also need lots of cells, called goblet cells, that produce these mucus so they can trap. But all of them together actually serve one singular function: to keep your respiratory tract clear so that air can move in and out smoothly. We don't appreciate this until we fall ill with some sort of respiratory illness. Right now as I'm talking, I'm quite out of breath because I still have a lot of mucus trapped somewhere along the trachea in my various airways. Sometimes some of the medicine that doctors give, the medicine is to help to make your mucus a little bit more liquid. Because when you're too sticky, you don't have enough energy to cough it out. Very hard for your cilia to sweep up all the mucus. Sometimes you need to liquefy the mucus a little bit. Then it comes out easier. all the way down to the ends of your respiratory tract. Notice that it stops somewhere at the bronchial level. Yeah? You also will not find these cilia and goblet cells at the air sacs, the alveoli. Okay, you will not find all these cilia, hair, mucus, goblet cells at the air sacs, the alveoli area. Because at the alveoli area is where oxygen and carbon dioxide really exchanges. So we need to keep things, we need to make sure our cells there aren't of this nature. When I was in secondary school, I got this illness called bronchitis. Anyone got before? No? It's good. The feeling is very terrible. I really felt I was drowning even though I was taking normal breaths. I could breathe normally, right? Air was going in, air was going out. But it felt like no matter how much I was breathing, I felt dizzy, I feel like out of breath all the time. So bronchitis is an illness where the cells, all the goblet cells, all the epithelial cells of the bronchus, the bronchioles, get inflamed, get infected. So mine was infected by what? Bacteria. So bacteria is infected all the way, trachea, bronchioles, bronchi, all infected. And when they are infected, you know what's the response of the body? All of your goblet cells, in response to all these bacteria, it will produce mucus like crazy. But when it produces mucus excessively, it will start to clog up every part of your airway. So for myself, I was taking breaths in, but I suspect it was just going down the trachea, but not quite going down anymore through the bronchi to the air sacs. Practically at night also cannot sleep properly because I was just not really getting air through all the way. So the doctor prescribed me some sort of medicine that helps to liquefy all of my mucus. Then next morning, right, everything came out. A very liquid version of the mucus. Then I could finally breathe again. But I'm sharing with you all this so that you can know how to prevent getting bronchitis. If you ever go to the swimming pool, or you go for a swim, or you get wet in the rain, make sure you don't go onto a bus, or you go to a cold place, and you don't change out your clothes. Because when you don't change out your clothes, when you are very, very wet and you get very cold, you can get the bacterial infections, there's high risk of bacterial infection. So last time I was in canoeing. After canoeing, I come up from the reservoir, I have this bad habit, I don't change. I just, with my wet clothes, I just board the bus, take a few stops down and go home. But I did that every day, until one day I fell ill with bronchitis. And then that became really tough on me. Okay, so that is the respiratory tract. That's the first part of the respiratory system. Remaining part of this lesson, let's look at some parts, the other parts of the system that is more important to help you breathe. Notice that these parts that we just talked about, not exactly responsible for your breathing mechanism. All this serves as no more than a tract for air to go in and out. But how do we even get air in and out of our system? That was your SLS work, what you're supposed to learn by yourselves. My role today is to fill in the blanks. Some areas that you may not have captured or you did not quite understand. So let's look at the various parts that are required for breathing. Okay, no longer respiratory tract, but your breathing mechanism. When you look at your breathing mechanism, there are a few things that come to mind. Your rib cage. Yeah? All of you can feel your rib cage. I forgot how many ribs we actually have. All your ribs connect to a point in the middle. You feel this part over here. This part over here is the sternum. The sternum is the part of your rib that connects all the various ribs together. What do your ribs connect to at the back? And your spine. So your ribs connect to your spine. They connect frontally to the sternum, dorsally. I think dorsally means back, to your spine. So that's how they connect together and hold up. There are also muscles. And the word to describe those muscles are, okay, I hope y'all can spell it well. I had a lot of trouble when I was a student spelling this. Costal muscles. Correct, no? It's not post, right? I think it's costal. confusion came in for myself when you include two more words in front. You have either internal intercostal muscles or external intercostal muscles. Yeah? I find some students will end up saying internal costal muscles. Yeah? But separate it out as internal intercostal muscles, not internal costal muscles. Okay, so just separate it out. You can actually feel your external intercostal muscles. Your ribs, right? It's not like in between your ribs you can just stick your finger through and touch your lungs, right? Instead, in between each rib, you can feel muscle. The muscles that you are feeling immediately between each rib, those are the external intercostal muscles. The internal intercostal muscles are the ones you cannot feel. They are wrapped on the inside of your muscle, of your skeleton. So if I look at your rib from the side view, let's say this is your rib, one rib right from the side view, two ribs, top and bottom rib. Your external intercostal muscles are the muscles that connect like that on the outside. Those are the ones you are feeling. The internal ones are on the inside, the ones that you cannot touch. These muscles are very important to help you understand how your ribs are able to swing out and in as you breathe. Yes, Isabel? Which one? Oh, this is your rib. If I cut it from the side view, let's draw in 3D. So let's say your rib. Okay, this doesn't help. Let's say, okay. So this is your ribs, your sternum, your ribs. Okay, imagine you only have two ribs. Okay, if I were to cut it down like that, and then I look at it from the side view, yeah. So the muscles that you feel immediately, those are the external intercostal muscles. There's another layer underneath. The layer underneath will be the internal ones. So that's what I was trying to draw. There's one layer that's internal, and then there's one layer that's external. Okay? So that is quite critical to help you understand how you're able to control the movement of your ribs when you breathe in and out. When you breathe in, notice that your ribs are moving up and out. When you breathe out, your ribs swing back down. Yeah? I saw, based on the answers that you provided on SLS, that you can sort of match things together. But I hope that you understand exactly how the mechanisms work. Here is a model that I've built, trying to make sense of how our ribs work, to breathe in and out. So now imagine that this is the side view. Imagine this is me at the side view. This is my spine behind, my sternum in front, and these are two ribs. One rib on top, one rib below. Okay? I've shortened it totally. By right, you have many more ribs. Okay? See following? You have external intercostal muscles, and you have internal intercostal muscles. Yeah? Because I was trying to make sense. I think in your SLS you have learned that when one set of muscles contract or relax, your ribs will either swing up or out. Then another one contract or relax, you will swing back down, correct? But which one is supposed to happen for which? As a student, I always just blindly memorize. But actually there is some logic to how it works. It all boils down to the muscles. So we look at this over here, ribs over here. If you want to breathe in, and you take a deep breath in, notice that your ribs swing up and out. Actually the muscles that you are using is this muscle over here. All muscles have an origin point and an insertion point. The origin point is where it branches out from. Insertion point is where it hooks on. It is at the insertion point where it contracts towards. It is at the origin point where it will contract towards. So this muscle over here, the origin is here, the insertion is here. If it were to contract, it's going to contract and shorten this way in. But notice that when this external intercostal muscle contracts, my rib cage swings up and out. Yeah? So actually there's a logic to the muscles working. External intercostal muscles, when I contract my external muscles, my rib cage swings up and out. Okay, breathe in, breathe out, just let go. Okay, breathe in, and let go. Okay, so when I breathe in, my external intercostal muscles are contracting. What about my internal ones? They're just in their relaxed state. Okay, they're just in their relaxed state. This one shortens, while the internal one just relax and lengthens fully, so that you can breathe in. Question, Isabel? Oh, where's the sternum or what's the sternum? Where's the sternum? This is the sternum. Your sternum is this over in the front. So if this is the front view, your sternum, all the ribs, and then your spine. Now I'm looking at this whole setup from the side view. Yeah? And this is my sternum, this is my ribs from the side view, and this is my spine from the back. So when I need to breathe in and I want my ribs to swing up and out, I need my external intercostal muscles to contract so that I can bring my ribs up and out. Yeah? What if you want to breathe out? Notice that breathing out is a process of just relaxing. You breathe in, requires effort, right? Breathe in, effort. But when you breathe out, all you have to do is to just let go. Right? You try now, you breathe in. When you breathe out, you just let go everything, right? You just relax everything. So actually when you are breathing out passively or in a relaxed way, all you are doing is to let every single muscle relax. My external one relax, my internal one is also in this relaxed state. Breathing out is a very relaxing process. Still following?
Do the internal intercostal muscles like contract at the same time?
Okay, then we have not spoken about the internal one. What about the internal one? I said that the external one can contract, right? We contract the external one when you're breathing in. Swing the rib cage up and out. When you breathe out, you just let both set of muscles relax. Then why the words the internal one fall then? It must be able to contract. Okay, it contracts when you want to breathe out forcefully. Notice that you can breathe out forcefully too. So you try now, you breathe in, and now when you force the breath out. Right? You can breathe out forcefully too, right? With effort. Alternatively, you could breathe in, just relax and breathe out. But can you breathe out a little bit more? Can, right? Can breathe out a little bit more with effort, right? In both instances, if you want to breathe out with effort, this is what you could do. You could contract your internal intercostal muscles, because the internal intercostal muscles are originate and insert differently. They originate from the bottom, they insert on the top. And so when the internal muscles contract, they contract downwards. When they contract like that. And so helps to explain why when you're breathing out, your rib cage comes back down. Yeah? So now there are three ways you could breathe in and out. Number one, when you're breathing in, always requires some sort of effort. When you breathe in, external contracts. Internal one is in its relaxed state. If you were to breathe out in a relaxed way, passively as they will call it, both set of muscles just relax. But if you want to breathe in, breathe back, if you want to breathe back out in an exerted way, what you could do is that as you're breathing out, you contract the internal muscles as well. I do not do both at once. Okay, so there are two ways you could breathe out. One, you could just breathe out using just the recoil action of your lungs. Or you could breathe out using the internal intercostal muscles contracting. But you only do that when you want to breathe out forcefully. For example, when do you breathe out forcefully? For example, if you are coughing. When you're coughing, you want to get things out, right? Just by letting your lung rib cage swing back down in a relaxed way, it's not going to cut it. You want the additional force. So your internal intercostal muscles will contract to give you the additional force to cough out. So there's some logic in how your ribs work and how the muscles work. And it works if you understand how the muscles contract and relax. I like to use rubber band because it also demonstrates that actually breathing out as a process can be a relaxed process. Don't need to use any contraction of muscles, just let it spring back into place. Just like what you are really doing. After you breathe in, you just let your ribcage spring back into place. Yeah, there's enough connective tissue to bring things back. Only if you want to put effort to breathe out, then you have to contract your internal muscles. Following? Let me tell you about a story when I broke my ribs. It's a very silly story of how I broke my ribs. First, I was showering and there's a bathtub. Then I thought to myself, hey, why don't I clean myself as well as the toilet at the same time? So I took a mop with a lot of soap. So I was like standing in the bathtub, and I was standing up here, and then I was like trying to mop the floor as I was showering, as water was coming on me. But then as I was doing it halfway, right, I slipped off. As I slipped, right, my whole ribcage just fell to the side of the bathtub. I felt excruciating pain. For a few days, it felt like there was nothing wrong. But as the days progressed, right, the pain got sharper and sharper and sharper. I went to the doctor and said I fractured my ribs. And I tell you what, when you fracture your ribs, can you imagine how if these two ribs are slightly out of place and misaligned, right? All the muscle fibers that are connected, right, also cannot function and contract, relax properly. Every breath I took, every message I said, I cough, sneeze, I laugh, right? Extremely painful. So more of the story is, don't try and clean your toilet when you're in the bathtub. And don't break your ribs up. Okay? But actually when I broke my ribs, right, I asked the doctor, is there anything you can do? Give me a cast or something. They said no. Unlike when you break your arm, right, you can put a cast, right? You break your ribs, right? Then you're going to put a cast, right? So actually, no cast. After I fractured my ribs, they say just live on your life and endure the pain. I can give you painkillers, that's it. Because with your other ribs still in place, it can still hold up so that your ribs slowly heal back in place. Okay? Next lesson, we'll talk a little bit more about the diaphragm. The other muscle that is responsible to help you breathe. Okay, I built a more epic version of what you're supposed to do. And I just put the diaphragm. But it's a serious problem because if you break the diaphragm, your lungs will not function anymore the same way they do. Okay, that's all for today.